Okay, hi everyone. This is the second video of the 13th week when we will briefly discuss approaches for network sampling and what do we know about that. And as you will see, I will highlight some of the results from basically three different streams of scientific literature. First will be approaches that come from social sciences or from sociology that are basically intended for sampling hidden populations using the network structure. Then we have a second stream of literature that deals with self-similarity of the networks, fractal structure of networks, and so on. And finally, maybe more a computer science perspective on network sampling, when we will discuss different classical approaches for sampling and what kind of biases do they give. I should also say that sampling is currently one of unsolved problems in network science. We know that most of the networks that we analyze are merely samples of their true variants, and we know that the samples are biased, so the structure will not be the same as of the original network, and in most cases we do not know how to correct for that. So let us first look at the first slide. So, as I said, the first stream of literature that deals with sampling comes from some social sciences. And approaches developed there are called like snowball sampling, contact tracing, respondent-driven sampling, and so on. And these are primarily intended for sampling some properties or revealing properties of some hidden populations. And what do I mean by hidden populations? This would be, for instance, some drug users, illegal immigrants, or things like that. When the population is relatively small and hard to tackle. So one approach is that we try to use their social network to actually sample that hidden population. So let's first talk about this first bullet here. So if you move to the next slide, imagine that you want to get some relevant information, some statistical properties of these hidden populations, for instance, drug users. And imagine that that the investigator by telephone calls a random person from a phone book and asks that person if he or she is a drug user. As you may assume, it's very unlikely that he will get a useful result. So for that reason, people have developed different techniques how to still sample these populations based on their social structure, social network. And important thing to highlight here that these approaches are not per se intended for sampling the network, but for getting some properties of a hidden population. However, we still get as a side effect a part of a social network of this hidden population. But you should make this distinction that per se these approaches are not intended for sampling. And the first approach mentioned on the slide is so-called snowball sampling. So what people do is that you first identify a single member of your hidden population, a single drug user, and you question him about things that you are interested in, and then ask him that he give you contacts to other members of this hidden population. So in a way, you're basically exploring their social network. And snowball sampling works like that you start with a simple single individual, then get all his or her contacts, then you question these contacts and get their contacts and so on. So in a way, from the computer science perspective, what you are actually doing is an example of simple breadth first search starting from some initial however, obviously, this sample of the entire social network is biased because it contains only the members of this hidden population. That would by itself be a biased sample. It is a very small part of the entire population and so on. It's possible to show that the probability that under the snowball sampling that you will reach a particular individual of this hidden population is proportional to the eigenvector centrality of the node in the entire network. So knowing the eigenvector centralities of the nodes, you could actually correct for any biases that you get. The problem is that in order for the things to saturate, you need a relatively large sample of the network so that the probability of sampling the node will really be proportional to its eigenvector centrality. However, the even worse problem here is that in order to compute the eigenvector centrality of a node, you by definition need the entire network, which we do not have because we are dealing only with the sample. So for that reason, there is really nothing that you can do here. You know that your sample is biased, you know how to correct for it, however you do not have that information. Nonetheless, this snowball sampling is probably the most popular approach in sociology for sampling hidden populations. And why it's called a snowball sample? Because on each way you get contacts of individuals and their contacts and so on. So you can imagine a small snowball that is rolling down the hill and it's getting larger and larger and larger, and the same thing will happen with your sample. So the first approach that we have discussed is simple snowball sampling that can be seen from the computer science perspective to be some breadth first search approach where the nodes are sampled according to their eigenvector centrality. If we go on, the next approach usually used in prevention of spreading of the diseases like the coronavirus and so on is so-called contact tracing. So imagine that a person comes to a hospital and is diagnosed and is positive for coronavirus. The authorities will make an effort to track down all the recent contacts of that individual and also test them for corona and so on until all leads have been exhausted. So in a way, the contact tracing is again, you could see it like a breadth first search technique. However, you're not including in your sample all the neighbors of a particular individual, but only those that were tested positive for corona. So then you explore their contacts and so on. So the nodes are basically sampled according to some hidden variable that we do not have direct access to, like being positive for coronavirus. So again, the sample will be biased, and we do not have a clear idea how to correct for that. And maybe from the computer science perspective, in order how to call this contact tracing in our terminology, maybe we could call it the best first sampling. So you're only exploring a couple of contacts of each individual, those that are positive. So best first here means disease first or so on. So maybe the best is not the most appropriate example. Okay, Okay, so we discussed snowball sampling and contact tracing. The last approach highlighted on the slide is so-called respondent-driven sampling. And this deals with some problems of both of the previous approaches. So imagine that you are trying to study the drug users, so you use one of these approaches, starting with some initial drug user, and then you trace its contacts and so on. It is reasonable to assume that the drug user will not be willing to tell you the names of the people with whom he was sharing a needle or something like that. And in many cases, simply asking for the contacts might be unethical, and authorities will prevent that, and so on. So an approach how to deal with that is called respondent-driven sampling. So you still first start with the initial individual, and usually a person is paid to some small amount of money to be willing to answer your questions, so that you can get some statistics and so on. Then you give some tickets to that individual and tell him that give these tickets to your immediate friends, so your neighbors in your social network that are also drug users. And if a person comes back to you with a ticket, you know that he is a friend of the previous guy, so you know that there should be a link in your network. And you usually tell them, if they come back and also take the questionnaire, both the neighbor and the original guy will be paid some small amount of money. So in order to motivate people to actually take your questionnaire. And the most important thing here is that people are just exchanging these tickets, so nobody has to reveal their name in this process. So the population still remains hidden. Nobody needs to name names of their friends or contacts and so on. If you imagine that you give a single ticket to each of the people that come to take your questionnaire, the sampling approach in a way resembles a random walk. So you're starting with some individual, and then he will give a ticket to one of its neighbors, so you will then question that guy, and so on and so forth. So you're basically doing a random walk exploration. Assuming that the person will give a ticket to his random friend or acquaintance. And in that particular case, we know that in a random walk, the probability that you will come to a certain node under the random walk is proportional to the degree of the node. So knowing the degrees of the node, now you can actually correct for the sampling bias. And the degree is something that you actually can get, in contrast, for instance, like to eigenvector centrality. The only thing is that each of the people that you question should also estimate how many friends they have. So you take that estimate as to be their degree, and then you can correct for the sampling bias. And how will responder-driven sampling with a single ticket can be seen as to be similar to some random walk exploration, where nodes will be sampled proportional to their degrees. So any property then you are interested in, for instance, what is the average age of the drug users, or their gender, or some other properties, you can correct for the biases that come from sampling. And how would that look like? Imagine that you want to estimate some property of this hidden population denoted by x. And let's say that we want to get the expected value of x. This would be like, I don't know, gender, age, or anything else. In the classical estimation of average, what you would do is that you would simply average the values of the people that you encounter in your random walk. So you have a sum of the values of each of the nodes that you have encountered divided by the number of the nodes. So basically you count each node as 1. Now, however, we are more likely to come to a high degree node, and in order to correct for that, you can reweight these values of x. So each value of x will be weighted with a weight that will be the reciprocal value of the degree of the node. So you are now correcting for the fact that you are more likely to find a high degree node. And finally, in order to get proper average, you would have to sum these weights. And as you will see in the labs, this first estimate will give us a very biased value that will be completely wrong. However, this second estimate actually gives us a corrected estimate that will be very close to the true value. As an example, which we will also study in the labs, imagine that the thing that we want to measure is the average degree in the network. So the average number of contacts a single member of this hidden population has. So our x's here are actually the degrees. So the top part here, what we will get is the sum of the degrees multiplied by 1 divided by the degree. And at the bottom, we have the sum of 1 divided by the degree. And since these two terms cancel, what you get on the top is simply the number of people in your sample. Let's call that S. And at the bottom, I get the sum of the degrees to the power of -1. Now look at this formula. How would a classical average formula look like? You sum the degrees and you divide by S. If I look at this formula, it looks completely wrong. Like I have no idea how to compute the average. However, as it turns out, this is an unbiased average, and you will see in labs how different the results actually are. Okay, so this is basically it, what I wanted to say about the approaches that come from social sciences. And as I said, most popular technique will be simply snowball sampling. However, this random walk approach or respondent-driven sampling allows you to correct for the biases that you get and should probably be used more often in the literature. Okay, so we have now talked about this first bullet. Let us move to the last bullet, where we will simply study different approaches that we can think of for sampling a network and see how similar the sampled network is to the original network. And the main motivation here, or the main rationale here, is that anytime when we analyze some network, in most of the cases, we will only be dealing with a sample of that network. So if you're studying Facebook, you also only have a sample of the Facebook. If you're studying the web, you also are able to analyze only a sample of the web, and so on. So for that reason, it's interesting to see how biased the results will be as a consequence of sampling. And starting with some original network, you could think about some simple techniques how to sample the network. Maybe you randomly select some of the nodes or some of the links and take the induced graph on those nodes or link as your sampled network. Or maybe you can use some snowball sampling approach that we have discussed, which will be similar to some breadth first search sampling. Okay, here I have an overview of different sampling techniques that you should think of. The first category I will call random selection methods. When you randomly select some nodes or some links or some larger structures, and this selection can be biased to some extent, and then take a subgraph of these nodes or link as your sample. So this will be like some random node selection with or without induction, whether you take an induced graph after your sampling or not, as shown in these first three cases. Here we have an example of random node selection. Next is a random node selection where the high degree nodes are more likely to be selected, so random node selection by degree. Here we have an example of a random link selection and so on and so forth. So this I would call the random selection methods. The next category of methods I will call network exploration methods. And this will be some approaches similar to the snowball sampling or responder-driven sampling or random walks that we have talked before. So you start at some point at some part of the network at some individual node, and then you explore the neighborhood of that node in some particular way. Like here in the example, we are seeing an example of snowball sampling or a simple breadth first approach. So these approaches are somewhat different than like random selection because they explore the part of the network starting at one particular node. And the last group of methods that I will like to mention are so-called, let's call the merging or aggregation methods. When you take your initial network and, for instance, find communities in that network, then you aggregate all the nodes in a particular community into one super node, which will give you a super network which can be seen as a sample of your network. So for instance, in this particular example, we get two communities. Both of these two are represented as a single node in the sampled network, and then you create a link whether there was at least one link between the communities of the original network. Instead of detecting communities, you could use any other clustering approach from self-similarity and fractality literature. There are approaches usually called network renormalization, like some box covering or cluster growing approaches, which you can see as to be similar to some clustering technique. And this will be my last group of approaches that I want to mention that are conceptually different than the first two. And as you can see on the slide, I would kind of see random selection methods as some sparsification techniques. So you take your network, you take a couple of parts of your network, you randomly select a couple of parts of your network, so you make the network sparser, you make your data sparser. Next, the network exploration techniques, I see them as some classical network sampling techniques when you take your entire network and then take only a part of that network, some sample of that network, like for instance doing breadth search, so that's why I call them network sampling techniques. And finally, these merging or aggregation methods, maybe you can call them like some network simplification techniques when you take the entire network and under some technique, under some procedure, you basically simplify it, you make it smaller. Notice also that there are two other terms mentioned here, global and local. Let's say that you have a very homogeneous network, that structurally the network is very similar to itself in different parts. Then to get a sample, you can take some local part of that network, and it will give you a good estimate of the entire network. For that reason, I'm calling these exploration techniques to also be some local techniques. But on the other hand, imagine that you have a very heterogeneous network, that you have different structural properties in different parts of the network. So in order to get all this information into your sample, you would actually have to sample a little bit of network here, a little bit of network there, a little bit of network here, and a little bit of network there, in order to get a representative sample of the entire network. So for that reason, I'm calling these random selection techniques to be more global approaches. So in summary, if the structure of your network is very heterogeneous, then you need a little bit of everything to get a reasonable sample, where in contrast, where your network is very homogeneous, you can take some exploration technique to get a relevant sample of your network. Okay, so let us then look at some results, how these different classes of approaches perform in practice. Now, the first question that you have to answer is, how large should your sample be? I mean, the smaller the sample, the less likely it will well resemble the original network. So if you take a sample of 90% of the nodes, this will be, structure will probably be more similar to the true network than if you take just, I don't know, 1% of the nodes. So the quality of the sample will surely decrease with the size of the sample, and it's nothing that you can do about that. But this tells you nothing about how large this sample should then actually be. But there are some empirical results highlighted on the slide, is that for sizes of sample that are considerably larger than, say, 10 or 15% of the original network, sampled networks all look relatively similar. And further on, if you go to samples that are considerably smaller than 1% of the network, the differences between the methods are basically undistinguishable. All methods fail, all methods give you a very bad sample of your original network, and it's really hard to say which method is better or worse. So based on these results, most of the people that have studied network sampling in the literature usually sample the network to 10 or 15% of the original size. And this could be 10% of the nodes or 10% of the limbs or anything else. And this also, another thing that one could think of is also that if I take 90% of the entire network, this is not really sampling. I mean, I'm taking almost all the network. So I would say that if you're taking, let's say, more than 50% of your entire network, that is not like a real sampling approach. And this also goes in line with this result that you should sample the network to say 10 or 15%. But of course, this depends on the particular application. Okay, so we have talked about these first two bullets. And 5 years ago, we have done a lot of empirical experiments on how well these different sampling approaches perform. And in practice, the common result is that random selection and random exploration methods, so the first two categories, usually perform much better than aggregation methods. In general, for particular use cases, this might not be true, but in general, usually random selection or exploration approaches perform best. And what is also interesting is that this is independent of the type of the network. This claim holds whether you're dealing with social networks, with information networks, technological networks, and so on. And it does also not depend on the size of the network, whether you're dealing with networks with millions of nodes or with networks with only thousands of nodes. However, the things do change when you change the sample size, the absolute size of the sample. Because smaller the sample, worse the approaches will perform. And you can look for the empirical results in this paper here. Let's just look at one example. Here I have the degree distribution of some computer science citation network, I believe, that seem to follow a roughly straight line on a double logarithmic plot. So it's a scale-free network with a power law degree distribution. The best performing approach here was, I believe, based on balanced propagation. And you can see that the slope of the degree distribution of the sample network is very similar to the original network. Of course, the distribution shifts to the left because the network is smaller, the degrees are smaller, and so on. But if you would estimate the power law exponent of these distributions, you will get relatively similar results. And you can look here for some other examples of networks, and you can see the distributions of the original network, the best performing approach, second best performing approach, and finally also the worst performing approach. Okay. So, and finally, the last slide regarding these sampling techniques is a schematic representation of how well different approaches perform in practice, prepared by a former doctoral student of our department. And here in gray, you have different sampling approaches like breadth first search, random walk with induction, random selection of nodes by degree, random selection of links, and so on. And then in black boxes, you can see different structural properties of networks. And for each of these properties, like the average degree, the solid line corresponds to the approach that has the best performance, that gives you the most similar value. And the gray dashed line shows you the second best performing approach. So, and in practice, how you should use that is that if you know that your data is sampled according to one of these different approaches, like you know that the Facebook API allows you that kind of sampling, so you're basically doing, I don't know, breadth first search, you can see which properties will be well preserved. And also, if you have an influence on how to do actually the sampling, and your final wish is that you will well preserve the degree distribution of the network, for instance, you can then see which of the approaches should perform well. And the more detailed schematic representation of these results can be found in the doctoral thesis of Miliblatus. Okay, so we have discussed these first bullet here. Now what we are left is 2 slides regarding the network similarity, network fractality, but before that I will make a short break here and continue in a minute. So see you in a minute.